Hello, wonderful person, this is Anton, and in this video, we're going to discuss a major discovery involving one of the most elusive propositions by Albert Einstein, and specifically one of the propositions from his general theory of relativity that for a very long time was extremely difficult to prove. But this time, scientists were able to observe something extremely specific coming from a distant black hole that definitively proves it correct. And so here this distant black hole was seen twisting the fabric of space-time around itself as it spins. And it only became visible because of an unfortunate star that approached a little bit too close and became destroyed. So basically this was an example of a TDE, or a tidal disruption event. And so in this video, let's briefly talk about this concept of frame dragging, talk about what Einstein proposed approximately 100 years ago, and of course discuss this detection and this event. But I guess
5% of the matter in the universe. Astrophysicists say it's some mysterious stuff, very unlike the matter that we see around us. Probably some sort of new particle or a new force or a parallel universe. I wish this was a joke, but it isn't. A new paper now argues that dark matter might just be normal matter. And to add insult to injury, the idea isn't even new. It's been around for 40 years. It's just that no one paid much attention. Well, that's quite something. Let's have a look. Astrophysicists have a lot of observations that tell us that dark matter can't just be normal matter, or so we thought. The most important clue is that, well, it's dark. More precisely, it doesn't interact with electromagnetic radiation at all, neither with light in the visible part of the spectrum nor with radio waves. This immediately rules out most of the particles around us, because everything that has an electric charge interacts with electromagnetic radiation. The only particles that are left then in the standard model are the Higgs and the Z boson, but those are highly unstable, and the neutrinos are not heavy enough to properly form structures. Physicists have gone through these arguments in circles for decades and always concluded it needs to be a new particle. Preferably one with a catchy name that sounds good in grand proposals. But now they're having a second look at an idea that goes back to no other than Ed Witten in 1984. He suggested that quarks, the particles that make up protons and neutrons, could form bigger clumps. These clumps could be stable and they'd be electrically neutral, so they wouldn't interact with light. They'd be dark. They'd fit the bill.
Right now,
These
tomorrow
objects are
exists,
sometimes
not as possibility, as location. While you experience this moment as the present, physics suggests you're just consciousness crawling through a static four-dimensional structure where past, present and future are equally real. The universe doesn't flow. It sits there, eternal and complete, containing your birth and death simultaneously. This isn't philosophy, it's what relativity has been telling us for over a century, and most of us just haven't been listening. From Einstein's destruction of absolute time to quantum mechanics hiding the present moment, we're diving into why your sense of flowing time is a cosmic illusion. Watch until the end to understand why everything you'll ever experience already exists, frozen in the fabric of space-time. If this journey through the nature of time has left you questioning everything the way it has me, make sure to hit like and subscribe so that you are here as we dig deeper into this topic. Drop a comment with where you're watching from, what time it is there right now, your present moment, and whether you think your future is already written or still waiting to be created. I'm curious to know what you believe about the flow of time after hearing all this. Part 1. The future. Already exists? You felt it your entire life. Time moves forward. The past is gone. The future hasn't arrived yet. You're standing in the present right now, reading these words as reality unfolds around you. It's the most obvious thing in the world, except it might be completely wrong. What if I told you that tomorrow already exists? Not in some mystical sense, not as a prediction or a probability, but actually exists right now as real and solid as yesterday. What if the future is already there, waiting not to happen but to be experienced? And what if the only reason you can't see it is because your brain is playing the most elaborate trick evolution ever devised? This isn't philosophy. This isn't speculation. This is where mainstream physics has been pointing for over a century. Since 1905, when a patent clerk in Switzerland rewrote the rules of reality, scientists have been grappling with an uncomfortable truth. The universe doesn't work the way it feels. Time doesn't flow. It sits there, all of it, at once. They call it the block universe. Imagine space-time as a book sitting on a shelf. Every page exists simultaneously. The first chapter, the middle chapters, the ending. They're all there, bound together, complete. You're just reading one page at a time. That's your present moment. But your inability to flip ahead doesn't mean those pages don't exist. The book is already written. Your future is already printed. You just haven't read it yet. This challenges everything. If the future already exists, what happens to free will? What happens to causality? What happens to the very notion of change? These aren't abstract questions. They cut to the core of what it means to be conscious, to make decisions, to exist in what we perceive as a forward-flowing reality. And here's where it gets stranger. This idea doesn't come from fringe theorists or mystical philosophers. It comes directly from Einstein's relativity, one of the most tested and verified theories in all of science. The same equations that predict how GPS satellites need to adjust their clocks, the same framework that describes black holes and gravitational waves, they also suggest that past, present and future are all equally real. They're just different locations in a four-dimensional structure, different coordinates, not different states of existence. Think about space for a moment. Right now, Paris exists. You might not be there. You might never go there. But Paris is real, occupying a different set of spatial coordinates than wherever you are right now. The block universe says time works exactly the same way. Tomorrow exists, next year exists, the day you die exists. They're just at different temporal coordinates, different locations in time, but locations that exist nonetheless, as solid and real as Paris or Tokyo or any place you've never been. Your brain doesn't like this. Evolution didn't wire you to think this way. Your ancestors survived by tracking predators, anticipating threats, remembering where food was hidden. They needed a sense of before and after. They needed causality. They needed to feel like time was moving forward. So your consciousness constructs that feeling. It builds a narrative where you're sliding through time, where the past recedes behind you and the future approaches like a horizon. It's a useful illusion. It keeps you alive, but it's still an illusion. The evidence sits in the equations. Einstein showed that there's no universal now. Two observers moving at different speeds will disagree about what events are simultaneous. Not because one is wrong, both are right. Simultaneity depends on your reference frame. What you call now and what someone else calls now can be completely different slices through space-time, and there's no experiment that can prove one of you is correct. The universe doesn't pick sides. It doesn't privilege any particular moment as the present. This breaks our intuition completely. We want there to be one present moment, one slice of reality that's happening right now, while everything else is either gone or not yet real. But relativity says no. Every moment is someone's present. Every moment is equally valid, which means every moment is equally real. And if every moment is equally real, then the future must already exist somewhere in the four-dimensional structure of space-time. It's not approaching. It's not becoming. It's already there. You're just moving through it, or more accurately, your consciousness is processing one slice of it at a time, creating the sensation of flow where none exists. This isn't just theoretical abstraction. We're going to explore the actual physics. We're going to dig into why Einstein's relativity destroys the concept of universal time. We're going to examine how quantum mechanics adds its own bizarre twist to the story. We're going to look at what neuroscience tells us about how your brain constructs the feeling of now. And we're going to confront the latest developments in physics, from gravitational waves to cosmic structures, that keep reinforcing this strange truth. But here's the question that will haunt you. If the future already exists, if it's sitting there in space-time as real as the past, does that mean everything is predetermined? Is your life already written? Every choice you'll make, every word you'll speak, every moment of joy or sorrow? And if it is, what does that mean for who you are? We're about to step through the looking glass. On the other side, time doesn't flow. The future doesn't arrive. Reality doesn't unfold. It just sits there, eternal and unchanging, while your consciousness crawls through it like a spotlight illuminating one frame of an already completed film. Ready to question everything you thought you knew about existence? Let's begin. Part 2. Einstein's Relativity and the Death of Universal. Now. The year was 1905. Albert Einstein was 26 years old, working in a patent office, analysing applications for electromagnetic devices. In his spare time, he was dismantling the foundations of physics. He published 4 papers that year. Any one of them would have secured his legacy. Together they rewrote reality. The paper on special relativity killed absolute time. Not metaphorically, literally. Einstein showed that time itself depends on how you're moving, not your perception of time, not your measurement of time, time itself. Two people moving at different speeds experience time at different rates, and there's no privileged reference frame that can claim to measure true time. All frames are equally valid. This seems abstract until you grasp what it means for simultaneity. Imagine two events happening at different locations. Event A. A supernova explodes in a distant galaxy. Event B. You blink. To you, standing on Earth, these events might appear simultaneous. They happen at the same moment. But to an observer moving at a significant fraction of the speed of light relative to you, these same events are not simultaneous. One happens before the other, not because of signal delays or measurement errors, because the order of events itself depends on the observer's motion. There's no fact of the matter about which event happened first. Your reference frame says simultaneous. Their reference frame says A happened first. Another observer's reference frame says B happened first. All three of you are correct. The universe doesn't contain a hidden clock that determines the real order. The order is relative. This destroys the concept of universal now. If we can't agree on what's happening at the same time, then there's no single present moment that everyone shares. Your now includes events that someone else considers past or future. Their now includes events you think haven't happened yet. These aren't disagreements about observation. They're disagreements about reality itself, and relativity says both realities are valid. Think about what this means. Right now, from your reference frame, you have a certain definition of the present. It's a slice through space-time that includes everything happening simultaneously, according to your motion through the universe. But someone moving relative to you has a different slice. Their present includes events in your past and future, and there's no experiment you can perform to prove your slice is the correct one. So if there's no universal present, then what is time? Einstein's answer is geometric. Time is a dimension, like the 3 dimensions of space. Space-time is a 4-dimensional structure where events exist at specific coordinates, 3 spatial coordinates and 1 temporal coordinate. Just as you can move through space by changing your location, you can move through time by changing your temporal coordinate. But the structure itself doesn't flow. It doesn't change. It sits there, complete, containing all events that ever were or will be. This is profoundly different from intuition. Intuition tells you that only the present is real. The past is gone, dissolved into memory and fossils and recordings. The future is unformed, genuinely open, not yet crystallized into actuality. You feel like you're surfing the leading edge of creation, the single moment where reality is actually happening. Everything else is either aftermath or potential. Relativity says that's an illusion, a convincing one certainly, an evolutionarily useful one, absolutely, but an illusion nonetheless. The equations don't care about your feelings. They describe a universe where past, present and future are all equally existent, just at different coordinates in a static geometric structure. Here's where it gets concrete. Consider 2 events, your birth and your death. To you, right now, one is in the past and one is in the future. Your birth has already happened, your death hasn't. But according to relativity, there exists an observer moving at the right velocity for whom both events are equally in the past. They've already seen both. Both events exist in their previous light cone. Similarly, there's an observer for whom both events are in the future. Neither has happened yet from their perspective. And there's an observer for whom your birth is past but your death is present, happening right now. All these observers are equally valid. None is more correct than the others, which means both events must actually exist, not just in the sense of having happened or being destined to happen, but in the sense of being actual components of the space-time structure. Your death is already there, at specific coordinates, as real as your birth, as real as this moment. You just haven't reached those coordinates yet. This is the foundation of the block universe. It's called eternalism in philosophy. Every event that ever happens exists eternally at its space-time coordinates. Nothing comes into being. Nothing ceases to exist. The entire history of the universe, from the Big Bang to the heat death, is a single unchanging 4-dimensional object. You're not moving through time. You're a 4-dimensional object yourself, a world line that extends from your birth to your death, and your consciousness is somehow localized to experience one slice of that world line at a time. The implications are staggering. If the future already exists, then it's fixed. Not in the sense of being predetermined by past causes, but in the sense of already being there, already having existence. Every decision you'll make already exists at its temporal coordinates. Every word you'll speak, every person you'll meet, every moment of triumph or tragedy. It's all already there, encoded in the geometry of space-time. Does this mean you have no free will? That's a question we'll circle back to. For now, just sit with the physics.
called quark nuggets. Normal matter is made from up and down quarks. These are the two quarks with the lowest masses. But Witten figured out that if you have a lot of up and down quarks, this is not energetically the best state. You get a state that's energetically more favorable if you add some of the next heavier quarks, the strange quarks. And because this combination is energetically more favorable if the quark clump is large enough, it doesn't decay, it's stable. This is a particular type of quark nuggets called strangelets. The size of the strangelets is important for that to work. Small combinations of quarks with strange quarks are unstable. We know this because we can create those in particle colliders. But if Witten's maths is correct, and who really wants to question Witten's maths, then large chunks should be stable. We can't produce these large strangelets in particle colliders. There just aren't sufficiently many quarks in the collisions, but they could have been produced in the early universe. And because they're stable, they just remain there, sitting around, being dark and heavy. Indeed, even tiny strangelets are enormously heavy. If you had a strangelet the size of a tiny dust grain with a radius of about 10 micrometers, that'd weigh about a ton. Yes, you heard that right. If it had a radius of a centimeter, that'd be about 1 billion tons. You have to admit that quark nugget is an adorable name for something that might weigh a mountain. The idea first caused some excitement and then it caused some panic, because the quark matter with the strange quarks is energetically more favorable than the stuff that we are made of. Physicists worry that if you could make just one stable strangelet in a particle collider, it might start converting all our ordinary nuclear matter into strange matter and eat the entire Earth. It'd be a similar problem to chemical polymorphs that the science fiction story Ice 9 is about. Those fears turned out to be unfounded because we can't produce the stuff in colliders. Even if some of the strange matter came by from outer space, it can't convert the normal matter because that only works at super high densities. The idea that strangelets make up dark matter fell by the wayside because it relied on a specific assumption about the early universe that turned out to be wrong. You see, in the early universe, we have this soup of quarks and gluons called a quark-gluon plasma. The plasma cools, and at some point it starts to clump into smaller pieces like neutrons and protons. This is a phase transition, much like when water vapor condenses to droplets. Indeed, in the 1980s, physicists thought that the phase transition in the quark-gluon plasma is similar to that of water. It's what's called a first-order phase transition. And in such a transition, you can get big drops of those strangelets, which then just continue to sit around as dark matter. It then became clear, though, that the phase transition in the quark-gluon plasma just isn't first order. It's instead a rather well-behaved crossover, and that doesn't make bubbles to create the strangelets. Now, however, physicists are rethinking this for two reasons. The first is that they found that while a first-order phase transition would do the job, it isn't necessary. Even without bubbles, there can be strong correlations in the plasma that can allow large clusters to form. The second reason is that physicists have found that quark matter can do peculiar sort of superconductivity that conducts not electric charge, but color charge. It's called color superconductivity, and it enhances the stability of quark matter. Take this together, and it turns out that strangelets can form in the early universe after all. Theoretically, they could weigh anything from nanograms to asteroid scale. There are other types of quark nuggets that physicists are reconsidering now besides the strangelets. The next most popular one is one that's stabilized by axions. These axions are hypothetical particles that many physicists believe exist. It's somewhat difficult to make up dark matter just of axions. However, combine the axions with quark matter and it works nicely. Quark nuggets have some specific experimental signatures. The most obvious ones are that if they hit our planet or maybe the moon, they'd leave traces like little tunnels. If they hit stars or white dwarfs, they could also convert the nuclear matter, leaving behind stars that are oddly compact or white dwarfs with weird spectra. But basically, the signatures are subtle and difficult to find, which fits all too well with our observations, doesn't it? Well, if this idea is right, then the biggest problem in cosmology wasn't missing matter, it was missing attention. A few years ago, I received some ugly letters from a debt collection company. They threatened to sue me for ordering something online and then not paying it. Turned out that someone had stolen my private data. I managed to get out of this, but since then I've become very protective of my personal information, which is why I've signed up to Incogni, who've been sponsoring this video. Each time you open a website, it'll try to collect data about who you are and where you are and what other websites you've visited. Many firms then make money by selling your private information to data brokers. Most countries have laws against that, and you can ask for your data to be removed, but doing this takes up a lot of time. Incogni automates the process of getting you out of those databases. You sign up and they'll contact the big sinners, request that your personal
Einstein didn't set out to destroy free will or challenge our sense of agency. He was trying to reconcile mechanics with electromagnetism. The block universe was a consequence, an implication that fell out of the equations. And for over a century, physicists have been testing relativity, and it keeps passing. GPS satellites correct for relativistic time dilation. Particle accelerators see particles living longer when they're moving fast. Gravitational waves, detected in 2015, ripple through space-time exactly as Einstein predicted. The theory works. Which means we have to take its implications seriously, and one of those implications is that time doesn't flow, it sits there, eternal, complete, containing your entire life from beginning to end. What you call the future already exists, you just haven't experienced it yet, but it's out there, waiting, or more accurately, not waiting, just existing, always has been, always will be. Part 3. Quantum perspective, treating time as a state, not a sequence. Relativity shattered absolute time. Quantum mechanics shattered certainty itself. If relativity says the future already exists, quantum mechanics says it exists in a superposition of possibilities until the moment of observation collapses it into actuality. These two frameworks don't play well together. Reconciling them has been one of the grand challenges of theoretical physics for a century. In quantum mechanics, particles don't have definite properties until you measure them. An electron doesn't have a specific location. It exists as a probability cloud, a wave function that describes where it might be found if you look. Only when you make a measurement does the wave function collapse into a single outcome. Before that, the electron genuinely doesn't have a location. It's not that we don't know where it is, it's that where doesn't exist as a property until measurement forces it into being. This seems to contradict the block universe. If the future already exists, then outcomes are already determined. But quantum mechanics says outcomes aren't determined until observation. An electron will pass through one slit or the other in the famous double-slit experiment, but until you check, it passes through both, or neither, or exists in a superposition that defies classical description. How can this randomness coexist with a predetermined future? One answer is that they don't coexist. Some physicists argue the block universe is incompatible with quantum mechanics, that the future can't already exist if quantum events are genuinely random. But others disagree. They point out that randomness and determinism aren't the same as existence and non-existence. Just because an outcome is random doesn't mean it doesn't exist. It just means we can't predict it. Consider radioactive decay. A uranium atom will decay at some point, but quantum mechanics can only give you probabilities. It might decay in the next second or in a billion years. There's no doesn't exist. It just means we can't predict it. Consider radioactive decay. A uranium is a non-existence. Just because an outcome is random. But others disagree. Some physicists argue the block universe. One answer: how can this randomness coexist with a predetermined future? One answer is that they don't coexist. Some physicists argue the block universe is incompatible with quantum mechanics, that the future can't already exist if quantum events are genuinely random. But others disagree. They point out that randomness and determinism aren't the same as existence and non-existence. Just because an outcome is determinism aren't the same as existence and non-existence already exist if quantum events are genuinely random. But others disagree. They point out that randomness and determinism aren't the same as existence and non-existence. Just because an outcome is random doesn't mean it doesn't exist. It just means we can't predict it. Consider radioactive decay. A uranium atom will decay at some point, but quantum mechanics can only give you probabilities. It might decay in the next second or in a billion years. There's no hidden exist. It just means we can't predict it. Consider radioactive decay. A uranium atom will decay at some point, but quantum mechanics can only give you probabilities. It might decay in the next second or in a billion years. There's no hidden variable determining when it will happen. The decay is genuinely random. But in the block universe framework, there's a specific space-time coordinate where that decay occurs. It already exists at those coordinates. The randomness is in our inability to predict the view probabilities. It might decay in the next second or in a billion years. There's no hidden variable determining when it will happen. The decay is genuinely random. But in the block universe framework, there's a specific space-time coordinate where that decay occurs. It already exists at those coordinates. The randomness is in our inability to predict which coordinates, not in whether the event exists. This is where things get speculative and fascinating. Some researchers have explored treating time itself not as a flowing sequence of moments but as part of a single quantum state. Imagine the entire history of a quantum system from beginning to end as one unified state. You don't have a system that evolves through time. You have a timeless state that contains all correlations between different temporal coordinates. This is mathematically complex and philosophically strange. It's similar to how quantum mechanics treats space. A particle is philosophically strange. There's no hidden variable, but others disagree. They predict it. Consider radioactive decay. A uranium atom will decay at some point, but quantum mechanics can only give you probabilities. It might decay in the next second or in a billion years. There's no hidden variable It might decay in the next second or in a billion years. There's no hidden variable determining when it will happen. The decay is genuinely random. But in the block universe framework, it will happen. The decay is genuinely random. But in the block universe framework, there's a specific space-time coordinate where that decay occurs. It already exists at those coordinates. The randomness is in our inability to predict which coordinates, not in whether the event exists. This is where things get speculative and fascinating. Some researchers have explored treating time itself not as a flowing sequence of moments, fascinating, whether the event exists. This is where things get speculative and fascinating. Some researchers have explored treating time itself not as a flowing sequence of moments but as part of a single quantum state. Imagine the entire history of a quantum system from beginning to end as one unified state. You don't have a system that evolves through time. You have a timeless state that contains all correlations between different temporal coordinates. This is mathematically complex and philosophically strange. It's similar to how quantum mechanics treats space. A particle in a box doesn't have a location that changes as it bounces around. It has a wave function that describes its state across all locations simultaneously. Some interpretations of quantum mechanics apply the same logic to time. The particle doesn't have a state that changes moment by moment. It has a single state that spans all moments, containing correlations between its properties at different times. If this sounds abstract, that's because it is. We're at the frontier of theoretical physics, where mathematics outpaces intuition. But the core idea is this. Quantum mechanics doesn't necessarily contradict the block universe. It might actually support it, if we're willing to let go of our sequential view of time and embrace a more holistic picture, where time is just another dimension over which quantum states are defined. There's another angle here, decoherence. In quantum mechanics, systems can exist in superposition, but large systems interacting with their environment quickly collapse into definite states through a process called decoherence. Your entire macroscopic world is constantly decohering. By the time you observe anything, the quantum fuzziness has already resolved into classical definiteness. So while quantum mechanics allows for superposition and randomness at small scales, the world you experience is already collapsed into specific outcomes. In the block universe framework, all these collapsed outcomes exist at their respective spacetime coordinates. Yes, there was quantum randomness before the collapse, but once the collapse happens, the outcome is fixed at that coordinate, and from the perspective of spacetime as a whole, all those coordinates exist simultaneously. The randomness determined which branch of possibility became actual, but the actual outcome exists eternally at its coordinate. This is where interpretations of quantum mechanics matter. In the Copenhagen interpretation, wave function collapse is a real process that creates definite outcomes. In the many worlds interpretation, all possible outcomes exist in branching parallel universes. In the block universe context, Copenhagen is more compatible. Each quantum event has one outcome that becomes fixed at its spacetime coordinate. Many worlds would suggest a branching block universe, which is a whole different level of complexity. But here's what's important. None of this undermines the central insight from relativity that time doesn't have a universal now. Quantum mechanics adds uncertainty to which events will occur, but it doesn't restore a flowing present moment. Even in quantum mechanics, different observers can disagree about the order of space-like separated events. The lack of absolute simultaneity remains, and if there's no absolute simultaneity, there's no universal present. And if there's no universal present, then all moments have equal ontological status. They all exist. Some physicists go further. They argue that quantum entanglement, where particles remain correlated across vast distances, might actually be a correlation across time as well as space. Entangled particles measured at different times might be connected by the same underlying quantum state, suggesting that temporal separation isn't fundamentally different from spatial separation. It's all just coordinates in space-time, and quantum mechanics can link those coordinates in ways that defy our sequential intuitions. This is speculative, but it's grounded speculation. We're not making things up. We're following the mathematics where it leads. And where it leads is toward a picture of reality where time is not a flowing river carrying us from past to future, but a landscape, or better yet, a structure, where all moments coexist and consciousness somehow samples that structure sequentially. The question quantum mechanics forces us to confront is this. Does randomness mean the future doesn't exist? Or does it just mean the future exists in a way that wasn't determined by the past? There's a difference. Existence and predictability wasn't determined. Does randomness mean the future doesn't exist? Or does it just mean the future exists in a way that wasn't determined by the past? There's a difference. Existence and predictability are separate concepts. The future can be real without being knowable. It can be fixed without being determined. And quantum mechanics, strange as it is, might actually help us understand how that works. Part 4. Perception versus physics. Why conscious now is an illusion. Your brain is lying to you right now, not maliciously, constructively. It's building a world for you to inhabit, a coherent narrative of flowing time and continuous experience. But that narrative is a fabrication, a model assembled from delayed signals and neural processing.
I was
By the time
sleepy
you
once.
experience anything,
It was a long time ago. If you think I look tired, well, you better get your eyes checked, Buster. That's a certified WebMD diagnosable moment right there that something has gone awry with your peepers. Could a sleepy man do this? Checkmate. Point is, in my endless battle against insomnia, I happen to have stumbled across something interesting again this evening, and it pertains to last night's video about the $20 million reality TV show Twitch streamer fan production extravaganza, mansion, titties, beer, rock and roll, whatever else it was pitching itself as, called the $1 Million Fan Show. Well, I speculated that it was a big scam, and a lot of Twitch streamers had been publicly put on the website. Some had even made announcements about their endorsement of the $1 Million Fan Show, and nothing about it seemed legitimate. I'm not just going to regurgitate everything from last night's video. You can check that out if you want a deeper dive on everything that was wrong with it. But last night on stream, like 45 minutes after I posted the video, they took their website down. Then I was checking their other ancillary shit.
it's already in the past. Consider vision. When you Right now, 3,000 kilometers beneath South America, Earth's magnetic shield is turning against itself. The South Atlantic anomaly, a zone of weakness that used to be a mere curiosity, has doubled in size over the past decade and is now splitting into two separate lobes. Satellites crossing this region experience glitches, astronauts shelter in reinforced modules, and deep in Earth's core, reverse flux patches are doing something that shouldn't be possible, forcing magnetic field lines to plunge back inward, cancelling our defences from the inside out. Meanwhile, the North Magnetic Pole is racing towards Siberia faster than ever recorded, and the Sun just hit solar maximum. Something fundamental is changing, and we're only beginning to understand what. Stay with me, because by the end, you'll discover why scientists are calling this a cosmic emergency that could reshape our technological future. If you're as intrigued by these unfolding magnetic mysteries as I am, consider subscribing so you can follow along as scientists track these changes happening right now. Leave a comment letting me know where you're watching from, what time zone you're in, and what you think about these planetary scale shifts we're witnessing together. Part 1. The shield is changing before our eyes. Something is wrong with Earth's magnetic field, and it's happening faster than anyone expected. Right now, as you listen to this, satellites are threading through a zone of weakness stretching across South America and the South Atlantic Ocean. This zone, officially called the South Atlantic Anomaly, has been growing. Not slowly, not imperceptibly, but dramatically, measurably, alarmingly. In the span of just a decade, this magnetic dent has expanded to cover an area roughly half the size of continental Europe. Imagine a shield that has protected our planet for billions of years, suddenly developing a crack that keeps widening year after year, and you start to understand why scientists are no longer treating this as a curiosity. The South Atlantic anomaly was always there, lurking in our data, a known quirk of the geomagnetic field that engineers designed around. Satellite operators knew to expect a few glitches when their spacecraft crossed this region. Astronauts on the International Space Station would close the shutters on certain modules when passing overhead. It was manageable, it was predictable, it was stable. But stability, it turns out, was an illusion we told ourselves, while the numbers quietly shifted beneath our feet. Data from the European Space Agency's Swarm satellite constellation tells a different story now. These 3 identical satellites, launched in 2013 to map Earth's magnetic field with unprecedented precision, have been watching the anomaly morph in real time. When you look at your hands, you're seeing light that bounced off them, travelled to your eyes, got converted into electrical signals by your retinas, and was processed through multiple layers of neural circuitry before reaching your conscious awareness. This takes time, not much, maybe 50 milliseconds, but it's not instantaneous. You're always seeing the past. Even your own body exists in your past by the time you perceive it. Now extend this to everything. Every sound you hear is delayed by the time it takes for pressure waves to reach your ears and for your auditory cortex to process them. Every touch you feel is delayed by nerve conduction times. Your entire conscious experience is a reconstruction of events that already happened, assembled by your brain into a seamless flow that feels immediate but isn't. Your brain works hard to hide this from you. It synchronizes different sensory streams so that sounds and sights appear to occur together, even though they're processed at different speeds. It predicts where moving objects will be by the time you perceive them, compensating for processing delays. It creates a sense of continuity across the gaps when you blink. Your conscious experience isn't a live feed, it's an edited broadcast carefully crafted to feel real time, even though it's always running on tape delay. This is important because it reveals something fundamental about consciousness. Your sense of now is a construction. It's not a direct perception of the present moment. It's a model built by your brain from information about the recent past. And if your sense of now is constructed, then maybe your sense of time flowing is constructed too. Physics doesn't have a now. There's no equation in relativity that privileges the present moment. Time is a coordinate like the dimensions of space. Just as here isn't a special location in space, now isn't a special moment in time. What physics calls the present is just whatever slice of space-time you happen to be calculating from. It's a reference point, not a fundamental feature of reality. But consciousness feels different. You experience a vivid, immediate present. You feel time flowing from past to future. You remember yesterday but not tomorrow. This asymmetry is so powerful, so ingrained, that it seems impossible to imagine it being an illusion. Yet that's exactly what neuroscience and physics together suggest. The psychological arrow of time is tied to memory. You remember the past because your brain stores information about previous events. You don't remember the future because your brain hasn't stored that information yet. But this is a statement about information storage, not about the nature of time itself. The fact that you can't remember tomorrow doesn't mean tomorrow doesn't exist. It just means your brain doesn't have access to information about events at later temporal coordinates. Think about space again. You can't see what's happening in Paris right now if you're in New York. Your lack of visual access doesn't mean Paris doesn't exist. It means light from Paris hasn't reached you. The same logic applies to time. You can't remember tomorrow because information about tomorrow hasn't reached your current temporal coordinate. But that doesn't mean tomorrow isn't real. It might just mean it's somewhere else in space-time, inaccessible to your current position. Your brain evolved to create a sense of flowing time because that's useful. Your ancestors needed to anticipate threats, remember food locations, plan actions. They needed causality. They needed before and after. A creature that perceived all moments simultaneously would be paralyzed. It wouldn't know which moment to act in. So evolution built a mechanism that samples space-time sequentially, creating the illusion of a moving present that carves future into past. But it's an illusion in the same way that the solidity of this table is an illusion. The table is mostly empty space, electrons and nuclei with vast gaps between them. But it feels solid because your sensory systems evolved to perceive it that way. Similarly, time feels like it flows because your consciousness evolved to perceive it that way. The underlying reality is a four-dimensional structure where all moments coexist. Your consciousness just experiences one slice at a time. This is where block universe meets neuroscience. The block doesn't need consciousness to exist. It's a geometric structure. But consciousness explains why we experience the block sequentially instead of simultaneously. Your consciousness is somehow localized to a particular set of temporal coordinates at any given moment, creating the experience of being in the present. As you move along your world line, or as your world line simply extends through space-time, your consciousness experiences different coordinates in sequence. That sequential experience generates the feeling of flow. Does this mean free will is impossible? If every moment already exists, if your choices tomorrow are already fixed at their coordinates, how can you be making free decisions? This is the existential question the block universe forces on us. And the answer isn't simple. Some argue that fixed doesn't mean determined by external forces. Your choices are fixed in the sense that they exist at specific coordinates, but they're still your choices, generated by your deliberation and values. The fact that they exist eternally doesn't negate the causal role of your decision-making process. Others bite the bullet and say free will is indeed an illusion, another construct of consciousness like the flowing present. You feel like you're choosing, but the outcome was always going to be what it is, not because someone or something predetermined it, but because it simply exists at those space-time coordinates. This is uncomfortable. Most people don't like being told their choices aren't real. But most people also don't like being told the future already exists. The block universe doesn't care what we like. What's fascinating is that physics and neuroscience converge on the same conclusion from different directions. Physics says time is a dimension, and all moments exist. Neuroscience says our experience of flowing time is a constructed narrative. Together, they suggest that the present moment, the feeling of now, the sensation of time passing, these are features of consciousness, not features of the universe. Reality is timeless. We are time-bound, or more accurately, we experience ourselves as time-bound, even though we exist as four-dimensional objects in a timeless structure. And if that's true, then everything you'll ever do is already out there. Not waiting to happen, just happening, at its coordinates, forever. Part 5. Breaking news, gravity, space-time, and new physics challenges. The year is 2025. Scientists have just detected something extraordinary in the fabric of space-time itself. Frame dragging around massive rotating objects has been measured with unprecedented precision. General relativity, Einstein's description of gravity as the curvature of space-time, continues to pass every test thrown at it. A century after publication, it remains one of the most accurate theories in physics. But accuracy doesn't mean completeness. Einstein's field equations describe how mass and energy curve space-time, how that curvature guides the motion of matter, creating what we perceive as gravity. Yet general relativity is famously incompatible with quantum mechanics. At the smallest scales, at the highest energies, near singularities, the equations break down. This tells us there's something deeper, some more fundamental description of spacetime that we haven't grasped yet. Recent observations push this further. Dark energy, the mysterious force accelerating cosmic expansion, remains unexplained. Dark matter, the invisible mass holding galaxies together, eludes detection. Both suggest our understanding of spacetime might be incomplete. New theories propose modifications to general relativity, tweaks to the field equations that could explain these phenomena without invoking invisible substances. Some of these modifications have implications for time. If spacetime can be curved by mass, if it can be warped and stretched, then maybe the geometry of time itself is more flexible than we thought. Maybe the block universe isn't uniform. Maybe some regions of spacetime have different temporal structures than others. Near a black hole, time dilates dramatically. An observer falling in experiences time differently than someone watching from a safe distance. If time can stretch and compress based on gravity, what does that mean for the simultaneity of events across cosmic distances? Frame dragging is particularly interesting. When a massive object rotates, it drags space-time around with it. Satellites orbiting Earth experience this effect. Their motion is influenced not just by Earth's mass, but by Earth's rotation twisting space-time itself. This is a prediction of general relativity that's been confirmed repeatedly. But it reveals something profound. Space-time isn't a static stage on which events occur. It's a dynamic entity that responds to matter and energy. Yet even this dynamic space-time might still be a block. The curvature changes with the distribution of mass and energy, but all those changes, all those curvatures exist eternally at their respective coordinates. The four-dimensional structure contains all the warping and stretching caused by every mass that ever existed. It's not that space-time flows and changes. It's that the block itself is curved in complex ways that reflect the distribution of matter and energy throughout all of space and time. Gravitational waves demonstrate this beautifully. When massive objects like black holes merge, they create ripples in space-time that propagate outward at the speed of the light. LIGO and Virgo detectors have measured these ripples, confirming another prediction of general relativity. But here's the thing. Those ripples aren't disturbances moving through a medium. They're distortions of space-time itself, and in the block universe framework, those distortions exist eternally at their coordinates. The wave passes through our position in space-time at a specific moment, but from the perspective of space-time as a whole, the entire wave, from source to eternity, is a permanent feature of the geometry. This is where new physics comes in. Some theories propose that space-time isn't fundamental. It might emerge from something more basic, perhaps quantum information or entanglement networks. If space-time emerges, then maybe time itself is an emergent property, not a fundamental dimension. This would be consistent with the block universe in a strange way. Time would be a useful approximation at large scales, but not a fundamental feature of reality. Other theories suggest extra dimensions beyond the four we're familiar with. String theory, for instance, requires 10 dimensions. Most of these extra dimensions are supposedly compactified, curled up so small we can't detect them. But what if some of those dimensions are temporal? What if there are multiple time dimensions, each with its own structure? This is highly speculative, but it would radically change our understanding of the block universe. Instead of a four-dimensional block, reality might be a structure with multiple temporal axes, and our experience of linear time might be a projection through one of those axes. These ideas are at the cutting edge. Many haven't been tested, some might be untestable with current technology, but they all share a common thread. They challenge our intuitive notions of space and time. They suggest that reality's structure is far stranger than everyday experience reveals. And they consistently undermine the idea of a privileged present moment or a flowing time. Recent advances in quantum gravity research strengthen this. Observations from gamma-ray bursts confirm that the speed of light is constant across enormous energy ranges, exactly as special relativity predicts. This reinforces the foundations on which the block universe rests. If relativity continues to pass tests, if its predictions continue to be verified, then we have to take seriously the implications that follow from it. And one of those implications is eternalism. All moments exist. The universe revealed by modern physics is not the universe of common sense. It's a four-dimensional structure, curved and warped by matter and energy, possibly emergent from deeper quantum processes, potentially embedded in higher dimensional spaces we can't perceive. Your life is a world line threading through this structure. Every event you'll experience is a point on that world line, and the entire world line from birth to death might already be there, carved into the geometry of space-time by the same equations that govern stars and galaxies. Does this make you feel small, predetermined, trapped in a cosmic script? Or does it make you feel vast, knowing that your entire existence is a permanent feature of reality, as eternal as the structure of the universe itself? Either way, physics doesn't care about your feelings. It describes what is, and what is, apparently, is a block universe where your future is already written. Not by fate, not by gods, but by the simple fact that it exists at later temporal coordinates in the same way that distant stars exist at different spatial coordinates, all equally real, all equally there, forever. Part 6. Lesser known. Theoretical angles, multidimensional time. What if time has directions? Not metaphorically, actually. What if there are multiple axes of time, multiple dimensions of temporal extension, just as there are 3 dimensions of spatial extension? This isn't mainstream physics, it's speculative, sitting at the boundary between theoretical exploration and mathematical possibility. But it's grounded enough to be worth examining, because if time can have more than one dimension, everything we think we know about past and future explodes into something far more complex. The idea emerges from attempts to unify physics. String theory requires extra dimensions to be mathematically consistent. Most of these are spatial, but some theorists have explored what happens if you add extra temporal dimensions. The math works, at least in certain frameworks. But the implications are bizarre. With multiple time dimensions, causality becomes vastly more complicated. Events wouldn't just follow one another in a single sequence. They could be ordered along multiple temporal axes simultaneously. Imagine 2 dimensions of time. Call them T1 and T2. An event has coordinates in both. Moving forward in T1 might mean moving sideways in T2. The sequence of events you experience depends on which temporal direction you're moving through. Different observers could traverse space-time along different temporal trajectories, experiencing completely different sequences of events, even though they're moving through the same structure. This is almost impossible to visualize. Our brains evolved to handle 3 spatial dimensions and 1 time dimension. Adding another time dimension breaks our intuition completely, but mathematically it's not impossible. In fact, some versions of M-theory, the unification of different string theories, use multiple time-like dimensions in their formulations. These dimensions might be compactified or hidden in ways that make them imperceptible at everyday scales, but they could still exist as features of reality's deeper structure. Why would you add extra time dimensions? One reason is symmetry. Physics loves symmetry. The laws governing space and time have certain symmetries that become more elegant if you treat time and space on more equal footing. In relativity, space and time are already unified into space-time, but time still behaves differently from space. You can move freely through space in any direction, but you seem locked into moving forward through time. Multiple time dimensions might explain this asymmetry by suggesting that we're actually moving through a multidimensional temporal structure, but only perceive one of those dimensions. Another reason is to solve certain cosmological puzzles. The Big Bang, the apparent beginning of time, poses problems for physics. If time had a beginning, what came before? What caused time to start? These questions are difficult to answer in a single time framework, but with multiple time dimensions, the Big Bang might not be a beginning of all time, just a boundary in one temporal dimension. Other temporal dimensions could extend infinitely, allowing for physics before the Big Bang in a different temporal direction. This connects to the block universe in interesting ways. If time is already a dimension, adding more temporal dimensions just makes the block higher dimensional. Instead of a 4-dimensional structure, you'd have a 5-dimensional or 6-dimensional structure with multiple temporal coordinates. Your world line wouldn't be a 1-dimensional curve through 4-dimensional spacetime, it would be a more complex object threading through higher dimensional reality. And future wouldn't just mean later in time, it would mean a direction in temporal space that could vary depending on which temporal axis you're moving along. Does this make free will more plausible? Maybe. With multiple time dimensions, the rigid linearity of a single timeline breaks down. Events could be connected in more complex ways, allowing for branching or looping temporal structures that aren't possible in a single-time universe. But it doesn't necessarily restore agency. Even in multidimensional time, the structure could still be a fixed block, just a more complicated one. Your choices could still be encoded at specific coordinates, just now coordinates in a higher dimensional temporal space. The observational evidence for extra time dimensions is essentially zero. We haven't detected any phenomena that require them. This doesn't mean they don't exist. It might just mean they're hidden at scales we can't probe yet. High-energy particle collisions at the Large Hadron Collider have looked for signs of extra dimensions without finding any, but those searches are mostly focused on spatial dimensions. Temporal dimensions might leave different signatures, or none at all if they're structured in certain ways. Some theorists argue that consciousness might experience multiple time dimensions even if physics doesn't make them obvious. Your subjective sense of time could be a projection through multiple temporal axes, creating the illusion of a single timeline from a more complex underlying structure. This is wildly speculative, bordering on philosophy rather than physics. But it's the kind of speculation that becomes possible once you accept that time might be more than just a single dimension of before and after. The most intriguing aspect of multidimensional time is how it challenges our assumption that the future is singular. In single-time physics, the future is whatever happens at later temporal coordinates along the one-time axis. But with multiple time dimensions, future becomes ambiguous. Future in which temporal direction? Depending on your trajectory through multidimensional time, different events could count as your future. This creates a universe where the future isn't just unknown, it's fundamentally plural, with multiple possible temporal directions leading to different sets of events. Does this help with the block universe's determinism problem? Not really. Even with multiple time dimensions, if the entire structure exists as a fixed block, then all futures exist. All paths through temporal space are already there. You're still a world line, just a higher dimensional one, threading through a more complex block. The feeling of choosing your path might be even more illusory, because now you're not just moving forward, you're moving through a space with multiple temporal directions, and your trajectory is still encoded in the geometry of the structure. But here's the thought that haunts this entire discussion. What if time is even stranger than multiple dimensions? What if dimensionality itself is the wrong way to think about it? What if time is an emergent phenomenon, a pattern that arises from something more fundamental, that has no temporal character at all? That's where the deepest speculations lead, and that's where we realize how little we actually understand about the nature of reality. We've barely scratched the surface. The future might already exist, or it might exist in ways so alien to our intuition that already and exist don't even apply. Part 7. Arrow of Time and Time Symmetry, Chaos or Illusion. You remember yesterday. You don't remember tomorrow. This seems obvious, fundamental. The past is fixed, accessible through memory and records. The future is open, unknown, unformed. Time has a direction, an arrow. But here's the uncomfortable truth. The fundamental laws of physics don't have an arrow of time. They work equally well forward or backward. The asymmetry you experience is not built into reality at its deepest level. It emerges from somewhere else. Consider Newton's laws. If you film a planet orbiting a star and play the video backward, it still obeys Newton's laws. The equations don't care which direction time flows. Maxwell's equations for electromagnetism are time-symmetric. Schrödinger's equation in quantum mechanics is time-reversible. Even Einstein's field equations in general relativity treat time symmetrically. You can flip the sign of time in these equations and they still describe valid physics. So where does the arrow of time come from? Why do we remember the past but not the future? Why do eggs break but never spontaneously reassemble? Why does heat flow from hot to cold but never the reverse? The answer is thermodynamics. Specifically, the second law of thermodynamics, entropy increases. This is the only fundamental law of physics with a built-in direction. And it's not really fundamental, it's statistical. Entropy is a measure of disorder, or more precisely, the number of microscopic configurations that correspond to a macroscopic state. A broken egg has high entropy because there are many ways to arrange the molecules of a shattered shell and spilled yolk. An intact egg has low entropy because there are far fewer arrangements that constitute an unbroken structured egg. The second law says that systems tend to evolve toward higher entropy simply because high entropy states are vastly more probable than low entropy states. This gives time its direction. We remember the past because memory storage increases entropy. Forgetting is thermodynamically favoured. We see eggs break because broken states have higher entropy than intact states. But here's the key. This isn't a fundamental law. It's a statistical tendency. It's possible for entropy to decrease locally, for broken things to spontaneously reassemble. It's just spectacularly unlikely. The arrow of time is probabilistic, not absolute. In the block universe framework, this is important. The entire structure exists, past, present, and future, but entropy increases from one end to the other. Low entropy at the temporal coordinate we call the Big Bang. High entropy at the far future we call heat death. This gradient creates the illusion of time flowing from past to future. But the gradient itself is just a feature of the structure, not a process happening within it. The block doesn't flow toward higher entropy. It contains a gradient, and creatures living within that gradient experience it as an arrow of time. Think about a physical gradient, like a temperature gradient along a metal rod. One end is hot, the other cold. Heat flows from hot to cold, creating a direction in space. But the rod isn't flowing. The gradient is a static feature of the rod's structure. Time works the same way in the block universe. There's an entropy gradient from Big Bang to heat death. Processes unfold in ways that increase entropy, creating the sensation of time flowing in a direction. But the four-dimensional structure itself is static. The gradient is just how the structure is organized. This raises a question. Why was entropy low at the Big Bang? If entropy always increases, why did the universe start in a low entropy state? This is one of cosmology's deepest puzzles. Some theories invoke inflation, a period of rapid expansion in the universe's first moments. Inflation could have set up the low entropy initial conditions that allowed entropy to increase thereafter. But this just pushes the question back. Why was the universe in a state that allowed inflation? Other theories suggest that the Big Bang wasn't actually the beginning. It might be a bounce, a transition from a contracting phase to an expanding phase. In cyclic cosmologies, the universe undergoes infinite cycles of expansion and contraction, and entropy might reset or behave differently in each cycle. These are speculative ideas, but they're motivated by the need to explain why time has an arrow at all. Here's where it gets strange. In some regions of a sufficiently large universe, entropy could decrease by chance. Statistical fluctuations could create local pockets where broken eggs spontaneously reassemble, where heat flows from cold to hot, where time appears to run backward. Observers in such regions would experience a reversed arrow of time. They would remember what we call the future and forget what we call the past. To them, their time would flow normally. They wouldn't realize anything was reversed. Only by comparing to other regions would the reversal be apparent. This suggests that the arrow of time is not a global feature of the universe, but a local property of the region we inhabit. We experience time flowing from Big Bang to heat death because we exist in a region where entropy increases in that direction. But the block universe as a whole might contain regions with different arrows, or no arrow at all. Time's direction is a local phenomenon, like the curvature of space-time near a planet. It varies depending on where you are in the structure. Does this mean the arrow of time is an illusion? In a sense, yes. It's not built into the fundamental laws. It emerges from statistical tendencies and initial conditions. But it's a very strong illusion, one that governs all macroscopic processes. You will never see an egg spontaneously reassemble. You will never remember tomorrow. The thermodynamic arrow is so reliable that it might as well be fundamental, even though technically it isn't. And this brings us back to the block universe. If the arrow of time is just a gradient in the structure, then the structure itself is timeless. It doesn't prefer forward over backward. It contains all temporal directions equally. Your experience of moving from past to future is a consequence of following the entropy gradient. But the gradient doesn't flow. It sits there, a permanent feature of the four-dimensional geometry, and your consciousness slides along it, experiencing the gradient as motion. This is profoundly disorienting. It means time's arrow, the most fundamental aspect of your experience, is not fundamental to reality. It's an accident of cosmology, a side effect of low initial entropy. In a different universe, or a different region of this universe, time might have no arrow, or multiple arrows, or an arrow that points in a direction orthogonal to the one you experience. The future already exists, but the direction that counts as future is just the direction of increasing entropy, and entropy is just a statistical tendency. So the future is both fixed and arbitrary. fixed in that it exists at specific coordinates, arbitrary in that which direction counts as future depends on the entropy gradient. This is the vertigo of deep physics. The more you understand, the less sense anything makes, until you surrender intuition and let the mathematics carry you into territories where past and future are just labels we impose on a timeless structure. Part 8. Block universe versus growing block versus presentism debate. 3 philosophers walk into a bar. One orders a drink that already exists. One orders a drink that's growing into existence. One orders a drink that only exists while being poured. They're all describing time, and they all think the others are crazy. This is the metaphysical battleground where physics meets philosophy, and the stakes are nothing less than the nature of reality itself. Eternalism, or block universe, says past, present, and future are all equally real. Time is a dimension. Every event exists eternally at its space-time coordinates. You, as a 4-dimensional object, stretch from your birth to your death, and every moment of your life is equally real and always has been. This is what relativity suggests. It's the view we've been exploring. But it's not the only option, and its competitors have powerful arguments. Presentism says only the present is real. The past no longer exists. The future doesn't exist yet. There's a single moment of existence constantly moving forward, creating reality in its wake. Everything that seems to exist is confined to this moving present. The past is gone. The future is mere possibility. Only now is actual. This matches intuition. It feels like only the present is real. But presentism struggles with relativity. If there's no universal now, then what defines the present moment? Different observers would have different presents, which means presentism either requires a preferred reference frame, contradicting relativity, or it becomes incoherent. Growing block universe is a compromise. The past and present are real. The future is not. Reality is like a book being written. Every page that's been written exists permanently. But pages not yet written don't exist. Time genuinely passes. The present moment is the leading edge of existence, adding new events to the growing structure. This preserves some intuition about time's flow while accommodating the permanence of the past. But it also struggles with relativity. If different observers disagree about simultaneity, then they disagree about where the growing edge is. The block can't be growing in multiple incompatible directions at once. These aren't just abstract philosophical positions. They have implications for causality, free will, and the nature of existence. If eternalism is true, then your entire life is fixed. Every choice you'll make exists already at its coordinates. Free will becomes problematic. How can you choose differently than you do if your choice already exists at future temporal coordinates? Presentism and growing block preserve more intuitive notions of freedom by saying the future doesn't exist yet, leaving room for genuine openness in what will happen. But physics doesn't care about preserving intuition. Relativity points strongly toward eternalism, the relativity of simultaneity, the lack of absolute time, the treatment of time as a dimension. All of this is easiest to interpret as a block universe. Philosophers have tried to salvage presentism by proposing relativistic versions where each observer has their own present, but this leads to contradictions. Events that are in one observer's past might be in another's future, and if only the present is real, then the same event would be both real and unreal, which is incoherent. Growing block faces similar problems. If the block is growing, then there must be a universal edge, a boundary separating real events from unreal ones. But relativity says there's no universal boundary. Different observers would place the edge at different locations. The growing edge would have to be relative to the observer, which means reality itself would be relative to the observer. Some philosophers bite this bullet and accept relative reality, but most physicists find it more natural to accept eternalism and say all events are equally real regardless of the observer. Here's where the debate gets technical. Some philosophers argue that eternalism eliminates temporal becoming, the sense that reality is genuinely changing and evolving. If all moments exist eternally, then nothing really happens. There's no process, no flow, no dynamic quality to reality. It's just a static 4-dimensional object sitting there timelessly. Critics say this is absurd, that it denies the most obvious feature of reality, change. Eternalists respond that change is still real. It just doesn't mean what we think it means. Change isn't a process of becoming. It's a relation between different temporal coordinates. Things are different at different times, and that's what change is. An apple goes from green to red as it ripens. In the block universe, there's a region of space-time where the apple is green, and another region where it's red. The apple changes in the sense that its properties vary along its temporal extension. That's real change, even though the entire structure is static. This sounds like word games, but it's not. It's a genuine attempt to reconcile the mathematics of relativity with the phenomenology of experience. Relativity describes a block. Experience suggests flow. Eternalism says the flow is an illusion created by consciousness moving through the block. Presentism says the flow is real, and relativity needs reinterpretation. Growing block says flow is real, but creates permanence in its wake. No one has definitively settled this debate. Different physicists and philosophers prefer different views, but the consensus leans toward eternalism among physicists, not because they've proven it, but because it's the most straightforward interpretation of relativity. Every alternative requires adding complications or reinterpreting what relativity means. Occam's razor favours the simpler view. Take relativity at face value, accept that time is a dimension, conclude that all moments exist. Does this mean free will is impossible? That's the next layer of debate. Compatibilists argue that free will is compatible with determinism and even with eternalism. Your choices are free if they result from your deliberation and values, even if they exist eternally at their coordinates. Libertarians argue that genuine free will requires open futures, which means presentism or growing block. Hard determinists agree with eternalism and conclude that free will is indeed an illusion, a comforting fiction that makes us feel like we're more than passive characters in a cosmic script. The truth is we don't know. Physics tells us about the structure of space-time. It doesn't tell us about consciousness, choice, or experience. The gap between objective physical description and subjective lived reality is where these debates live, and that gap might never be fully bridged. We might always be left with a tension between what physics says is true and what experience tells us is real. The block universe is where that tension is most acute, because if it's true, then everything you'll ever do is already done, not in the sense of being predetermined by causes, but in the sense of already existing at its coordinates, fixed, eternal, there in the structure, and no amount of philosophical manoeuvring can make that feel comfortable. Part 9. Information, Memory, and the Fabric of Reality. Information is physical. This isn't a metaphor. It's a principle that emerged from 20th century physics and has become increasingly central to our understanding of reality. Information can't be destroyed. It has entropy. It bends space-time. Black holes store information on their surfaces. Quantum entanglement links information across vast distances. And if information is woven into the fabric of space-time itself, then past and future might be connected in ways far stranger than we imagined. The black hole information paradox crystallized this. When matter falls into a black hole, it carries information about its quantum state, its properties, its history. What happens to that information? Hawking showed that black holes evaporate through quantum radiation. Eventually they disappear completely. But the radiation Hawking calculated is thermal, random, carrying no information about what fell in. This suggests the information is destroyed, violating a fundamental principle of quantum mechanics. Physicists struggled with this for decades. Some propose that information is preserved in subtle correlations in the Hawking radiation, too complex to detect but mathematically present. Others suggested information might be stored at the black hole's event horizon, encoded holographically on a two-dimensional surface. This is where holography enters the picture. The idea that three-dimensional space might be a projection from information stored on a two-dimensional boundary. Holography has radical implications for space-time. If the universe is holographic, then the three-dimensional space we perceive is emergent, a kind of hologram projected from information on a distant boundary. Time might emerge the same way, not a fundamental dimension, but a construct arising from deeper quantum information dynamics. In this view, the block universe isn't fundamental either. It's an emergent structure, and the true nature of reality is timeless quantum information. Quantum entanglement adds another layer. When particles become entangled, their states are correlated. Measuring one instantly determines the outcome of measuring the other, regardless of the distance between them. Einstein called this spooky action at a distance, and thought it proved quantum mechanics was incomplete. But experiments have confirmed it. Entanglement is real. and it connects particles across space in ways that defy classical description. Some physicists argue entanglement also connects events across time. Particles measured at different times can be correlated through quantum states that span temporal as well as spatial separation. This suggests time might not be as separate from space as it seems. Correlations don't respect temporal ordering in the way classical causality demands. Entangled particles are linked by something deeper than cause and effect, and that something might be timeless quantum information. This is where information meets the block universe. If space-time emerges from quantum information, then the distinction between past, present, and future might be less fundamental than we think. Information exists timelessly in the underlying quantum state. What we call past and future are different slices through that state, different ways of organizing the information into a temporal sequence. But the information itself doesn't flow or change. It just is, encoding all correlations across all events, and our experience of time is a way of processing that information sequentially. Memory fits into this picture strangely. Your brain stores information about past events, creating the illusion that the past is special, more real than the future. But if all moments exist in the block universe, then future events are just as real as past ones. The asymmetry is in your access to information.
Hello wonderful person, this is Anton, and in this video we're going to discuss a major discovery involving one of the most elusive propositions by Albert Einstein, and specifically one of the propositions from his general theory of relativity that for a very long time was extremely difficult to prove. But this time scientists were able to observe something extremely specific coming from a distant black hole that definitively proves it correct. And so here this distant black hole was seen twisting the fabric of space-time around itself as it spins. And it only became visible because of an unfortunate star that approached a little bit too close and became destroyed. So basically this was an example of a TDE, or a tidal disruption event. And so in this video, let's briefly talk about this concept of frame dragging, talk about what Einstein proposed approximately 100 years ago, and of course discuss this detection and this event. But I guess let's start with the theory. So what is frame dragging and how can you actually visualize it? And so here let's try to understand this concept that's technically known as lens theory precession. And well, you can see the visualization of this in one of the videos by David Butler on YouTube. But to put it simply, according to Einstein, gravity is not just a force, it's essentially a curvature of space-time. And if you have a really massive object, especially a spinning object, so for example, a really massive black hole, it does not just sit there, it actually starts dragging the surrounding space along with it, just like you see in the simulation. And one of the ways of imagining this in real life is by basically taking a spoon and using honey. If you spin that spoon, the honey right next to the spoon starts to swirl with it. But as you move further away, the effect gets weaker and is a lot more difficult to observe. But the central swirl of honey is exactly what's happening to space extremely close to a massive rotating mass. In physics, this is often referred to as the gravitometric field. And so just as a rotating charged object creates a magnetic field, a rotating massive object creates a gravitomagnetic field that influences everything nearby. And well, the thing is, this has been proven many years ago by using the experiment you see in this video. But the thing is, the effect was incredibly subtle. It was actually so weak that it would take a pendulum approximately 16,000 years to shift by just 1 single degree. In other words, it could only be observed using extremely accurate measurements, which was done by this gravity probe B in the early 2000s. Here's roughly what the scientists discovered after several years of experiments. And this, of course, was the first proof that this lens theory effect, or the frame dragging effect, was real. So here, even planet Earth was actually dragging the space-time around itself just a little bit. But to really see this in action and to physically measure this, we obviously need something much more extreme, such as a supermassive black hole. And this is where we have this new discovery from 2020 of a very specific TDE, tidal disruption event. This was an event referred to as AT2020 AFHD, located in a galaxy approximately 400 million light years away from us. And it's an event involving a central supermassive black hole that basically shredded apart a star. Now, this is something we've seen many times before, but here the actual emissions were just a little bit different. So usually when a TDA occurs, a star moves a little bit too close to a black hole, and the immense gravitational pull creates such powerful tidal forces that it then shreds the star apart. And as a lot of the material falls into the black hole, it forms an extremely powerful and very hot accretion disk, with the rest of the material accelerated and shot out from very powerful jets at nearly the speed of light. You can learn about some of the recent discoveries about these events in some of the videos in the description. But what made this event so different was the unusual rhythmic heartbeat in the data. Basically here, the emissions from the black hole created a kind of a sinusoidal pattern, with all this eventually reported and described in a study you can find in the description. And well then, by using additional telescopes, such as the Swift Observatory and the Very Large Array, researchers observed X-rays and radio signals and discovered something unusual and something that was actually never seen before. They observed a very bizarre 20-day-long wobble. And first, researchers found that the X-ray signals coming from the disk and the radio signals coming from the jets seemed to be wobbling in unison. Basically, as one of